This screencast will show how to solve equations in the Laplace domain, or the S domain, which contain imaginary roots, and allow us to put them back into the time domain. To accomplish this, we'll use the equation shown on the screen here. To show the fact that this system in fact has imaginary roots, all we have to do is recognize the s squared plus 4s plus 5 part and realize that using the quadratic equation, if we look at the square root term of the quadratic equation, if this term is less than 0, that will tell us the fact that our roots are in fact imaginary. So when we do this, we have -4. So therefore what this shows is the fact that we have two imaginary roots. Processes which have imaginary roots are systems or processes which will oscillate in nature. From a mathematical standpoint, that represents the appearance of cosines and sines in our final solution. There are some processes such as swings and pendulums which naturally have this. However, most chemical processes do not have imaginary roots. Where we sometimes see the presence of imaginary roots in chemical process control is for some systems which are controlled using PID control, where it is possible to end up with imaginary roots. In fact, many tuning parameters take advantage of this fact and are tuned to ensure the fact that the process obeys quarter decay, which is an oscillatory response. Recall that systems with imaginary roots will have the form of A plus or minus BI. But the question now becomes is when we're trying to convert this from the Laplace domain to the time domain, what functional form should we have? And the best way to answer this question is to look at the Laplace transforms that are available. Looking at the transforms provided here, what you'll see is the fact that there are no I terms here, and the fact that everything is left in s squared plus omega squared, or s plus b squared plus omega squared. So therefore, we don't want to solve these using the value I, which is equal to the square root of -1. So our focus here will be to leave things in s squared plus 4s plus 5 terms. In other words, our focus is going to be looking at the last two equations I've shown here in order to eventually take the inverse Laplace transform. To do this, what we're going to have to do is use partial fractions. So what we'll do here is we'll just rewrite what we have above and then break it into its roots. And what we'll have here is a over s, but we don't want to break the other root because of the fact that we don't want to deal with i's, because the i's provide us no help in trying to use the Laplace transform table. But what this means is that the numerator of this will not just be a constant, but it'll be of the functional form bs plus c. To solve for a, b, and c, our focus will shift to the numerator. What we'll now do is find a least common factor and multiply the a by the s squared plus 4s plus 5 and the bs plus c term by s, of which this must equal the numerator we already have, 3s squared plus 5s plus 5. We'll provide that here. What you'll notice on the right-hand side is that the highest power of s that we have is s squared. So what we now want to do is break this down into terms with varying powers of s, and we have three of them here. We have s squared, we have s to the first, and we have s to the 0. In other words, the constant terms. So if we look at our right-hand side, we see that we have an as squared term and a bs squared term. If we look at our s terms, we have 1 for a, 4as, and we have 1 for c, c times s. For constant, the only one we have is 5a. We then use the left-hand side to match what these coefficients have to equal. So if we look on the left-hand side, we have 3s squared, 5s, and 5. We can now solve for a, b, and c using, first we'll start with the s to the 0th equation to find a. A equals 1. We can then substitute in a equals 1 to the s to the first term, and that will show that c also equals 1. And the s squared equation will allow us to solve for b. b equals 2. Now that we have solved for all of these constants, we can substitute them back into the equation shown above. When that substitution is done, the equation is the one shown here. The inverse Laplace transform for 1 over s is relatively straightforward. It's just the inverse of a step function, which is just a constant. That's 1. In order to take the inverse Laplace transform of the second term, we have to go back to our Laplace transform sheet. As noted before, our focus here will shift on the bottom two equations because we don't have a perfect s squared plus omega squared in our denominator. But what we now need to do is find b and omega. In order to do that, we have to complete the square of the denominator. So in order to complete the square, s squared plus 4s plus 5, in order to complete that square, what you do is you take half of the value for the s term, which is 4, and then take the square of it. So therefore that would be s squared plus 4s plus 4. You then add or subtract whatever the difference is with the original constant you had. So therefore originally we had a constant value of 5. We already have taken up 4, so therefore what we're left with is 1. The s squared plus 4s plus 4 will be a perfect square. In this case, it'll be half of the value of the constant, which was 4, so therefore this will become s plus 2 squared plus 1 is our new denominator. By mapping this to the Laplace transform sheet, we've shown the fact that b is 2 and that omega is equal to the square root of the constant term hanging outside, which in this case the value is 1, so the square root of that is also 1. But looking at this, we hit a little bit of a problem. If we are to substitute omega and b in, what we have is 1, and for this part here, we have s plus 2. The problem is that our numerator for this is 2s plus 1. So what we're going to have to do is find a way to turn 2s plus 1, our numerator, into a linear combination of the 1 and the s plus 2. There are a number of ways to approach determining what the constant should be in front of the two terms found in the Laplace transform sheet. One will be provided here. And the methodology works very similar to the concept of partial fractions, where we're having a linear combination of multiple terms such that the numerators are consistent. The easy thing here is the fact that they both have the same denominator, so we don't have to worry about that step. So if we look at what we have here, we have that 2s plus 1 is going to equal a plus bs plus 2b. By looking at this, we see the fact that the only s term on the right-hand side is bs, so therefore that tells us that b equals 2. And what's left with the constant terms is that a plus 2b equals 1, which means the fact that once we substitute in what b is, that tells us that a equals -3. So if we revisit our original equation, with the second term factored out to be more friendly for the Laplace transform table, we can see that when we take the inverse Laplace transform of our second term, that just corresponds to the sine term that we have here. So therefore this term becomes e to the negative bt, where b has been shown to be 2, multiplied by the sine of omega t, where here we showed that omega was 1. And then we include the constant -3. So for our third term, it will correspond to the cosine term, which will be e to the negative bt, which is still 2, multiplied by cosine of omega t, which in this case is still 1. We then add the coefficient to our system, and when we put these all together, we get our final answer, which is that y in the time domain equals 1 minus 3e to the negative 2t sine t plus 2e to the negative 2t cos t. So an important part of dealing with imaginary roots is that you ensure the fact that when you're trying to solve the problem, you are gearing it towards the Laplace transform sheet that you have available. Different transform sheets may show things in slightly different ways, so you're going to want to gear it towards the Laplace transform sheet that is available to you.